Hello, in this video, we will be dealing with conservation of momentum and energy collisions. Note that the learning objectives of this are the following: to learn the concepts of momentum and impulse, to know the conditions under which the total momentum of a system of particles is constant, to solve problems in which two or more bodies collide with each other, and lastly, to learn the important distinction among elastic, inelastic, and perfectly inelastic collisions. To start with, there are many questions involving forces that cannot be answered by directly applying Newton's second law. For example, when two moving cars collide head-on, what happens to the two and how does the impact affect the motion of each vehicle? Or in playing pool, how do you decide how to aim this cue ball in order to knock the eight ball in the pocket? Or when a meteorite collides with the Earth, how much of the meteorite's kinetic energy is released? Note, these questions can't be answered by directly applying Newton's second law, but simply answered by the concept of linear momentum. Well, linear momentum is the tendency of a moving body to continue moving and the difficulty it encounters in slowing down to rest, or sometimes called as inertia in motion. All objects have mass, so if an object is moving, then it has momentum. The amount of momentum is dependent on two variables such as mass and velocity. The SI unit for this one is in kilogram meter per second. It is a vector quantity and its direction is the same as the velocity vector. It can be expressed in terms of components such as x, y, and z. Note that a bus can have a large momentum even if it's moving very slowly because it has a large mass. Or a bullet can have a large momentum even if it has small mass because it is moving at a high velocity. But if an object is at rest, it has no momentum, no matter how massive an object is. Take note that momentum is not the same as inertia. For example, which has more momentum? A 1,200 kilogram steam ruler moving at 1 meter per second, or a 1 kilogram bullet moving at 1,200 meters per second? The answer will be both of them have the same momentum. If you'll try to calculate the momentum of each object by multiplying their mass and velocity, you'll yield the same answer. I want you to think about this. If the boulder and the boy have the same momentum, will the boulder crush the boy? The answer will be no. The boy has less mass, thus he will need to have much higher velocity in order to have the same momentum as the boulder with a much greater mass. Take note that momentum is a product of mass and velocity. For this case, momentum is constant. So you could able to say that your mass is inversely proportional to velocity. What does this mean? In order to yield the same amount of momentum for each object, if mass is large, then its velocity is slow. On the other hand, if mass is small, its velocity is fast. Remember the Newton's second law, which states that when a net external force acts on the object of mass m, that object will accelerate in the direction of the net force. Since acceleration is simply change of the velocity over time, so the Newton's second law can be written as of this form. We can substitute A into delta V over delta T. And since mass is a scalar quantity, we can place it adjacent to velocity. So take note that mv is simply the momentum. So we could state the Newton's second law in terms of momentum as the net force acting on an object is equal to the rate of change of the momentum of the body. Let's take for an example in a baseball game, when the pitcher throws the ball towards the batter, the ball's momentum changes over time due to the presence of the net external force. Likewise, when the batter hits the ball, the momentum again changes both in magnitude and direction. Again, the law of acceleration can be written in this form. Note that multiplying both sides by delta t cancels out the delta t on the left side of the equation, and we'll have the change of momentum is simply equal to the product of the net force and delta t, which gives rise to a new term, what we call as impulse. Well, impulse is a force applied for a period of time which results in a change of momentum. Take note that when momentum is constant, the impulse is zero. So the SI unit for this one is in Newton second or kilogram meter per second. Notice that impulse and momentum have the same unit, but take note when we say impulse, it means to say change in momentum. This equation here is also what we call as impulse momentum theorem, which states that the change in momentum of a body during a time interval is equal to the net force that acts on the body during the time interval. In order to increase the momentum of an object, we need to apply the greatest force for as long as possible. Just like a golfer teeing off and a baseball player trying for a home run, both of these things swing as hard as possible and follow through with their swing. On the other hand, in decreasing the momentum, just think about riding in an out of control car. Would you prefer hitting a haystack or a concrete wall? Hitting either of the two, the momentum is decreased by the same impulse. What do I mean? It does not mean the same amount of force or the same amount of time, but it means the same product of force and time. To keep the force small, of course, we need to extend the time. Here, if the change of momentum occurs for a very long time, the force of impact is small. But if the change of momentum occurs for a very short period of time, the force of impact is large. Consider an isolated system of two objects that interact each other. Internal forces between these two are being considered, in which each particle exerts force on the other. When we say internal forces, these are the forces that objects within the system exert on each other, while external forces are forces exerted on objects by agents external to the system. According to Newton's third law, the two forces are equal in magnitude but opposite in direction. Even the impulse, the change in momentum are both equal in magnitude but opposite in direction. So here, object 1 exerts force on 2, and its force is towards this direction. Even object 2 exerts force on 1 through this direction. So using the impulse momentum theorem for body 1, the change in momentum is simply equal to force exerted by 2 on 1 times the time. So when we say delta P or delta, it means to say change. It means to say final minus initial momentum. So for object 1, its final momentum is P1 prime. So you'll have initial P1, so you'll have P1 prime minus P1 is equal to F2 on 1 is equal to negative F. So substituting here. And on the other hand, for body 2, you'll have the change in momentum prime is equal to F1 on 2 and then delta T. So for body 2, you'll have the final momentum is P2 prime minus P2. So here, manipulating these two equations here by multiplying negative 1 both sides in this equation and rearranging the equations will give rise to the equation for the conservation of momentum. So in which the left side of the equation is the initial momentum of the system, which is equal to the left side is the final momentum of the whole system. So the condition for the conservation of momentum is that if the net external force is zero, so the total momentum of the system is constant. On the other hand, collision is any strong interaction between objects that lasts in a relatively short time. This time, forces between the interacting bodies are much larger than any external forces, and the total momentum of the system is conserved in any type of collision. So take note from the principle of conservation of momentum that if the net external force is zero, then the total momentum before the collision is equal to the total momentum after collision. So there are two types of collision. One is what we call as elastic collision, wherein the forces between bodies are also conservative. So both the momentum and the kinetic energy is conserved. And this one, objects just bounce off each other. There will be no deform or deformations, no heat or sound given off. On the other hand, for inelastic collision, this is where the total kinetic energy decreases after collision. So only the momentum is conserved. There will be distortions, heat and sound is given off. And if the objects become tangled or coupled, this is what we call as the perfectly inelastic collision. Again, for elastic collision, both the momentum and the kinetic energy is conserved. Take note that this equation here is applicable only for one-dimensional collision. The v here are the initial velocities of the particles, and the v primes are the final velocities of the particle. Also, manipulating these two equations here will yield an equation for both final velocities of the particles. And take note that this is only applicable for elastic collision. For completely inelastic collision, since the two stick together, so their final velocity is simply the same. So only the momentum is conserved for inelastic collision. One of the ways to determine the type of collision is to calculate for the coefficient of restitution, given by this equation. If E is equal to 1, then it's elastic collision. If E is greater than 0 and but less than 1, it's inelastic collision. And if the coefficient is equal to 0, then it's said to be perfectly inelastic collision.